What?
I didn't know about that.
What?
That's...
Oh, about the little armors thing. Yeah. Yeah, of course, the one next to me is gone.
All right, everyone. Welcome on this gorgeous sunny day to the Great Indoors. This event joint hosted by CFI Okanagan and University of British Columbia Okanagan Freethinkers. My name is Ian Cromwell. I am a member of CFI Vancouver. I'm also the author of the Crommunist Manifesto at Freethoughtblogs. I've been asked here today to moderate this panel, which should be a lot of fun. I hope everyone learns something new. The Center for Inquiry, for those of you not familiar with our organization, is an educational charity with a legal mandate to educate and provide training in the public application of skeptical, secular, rational, and humanistic inquiry through conferences, symposia, lectures, published works, the maintenance of a library, and also to develop communities where like-minded individuals can meet and share their experiences. CFI focuses its efforts on three broad areas, the first being religion, ethics, and society, the second being pseudoscience, paranormal and fringe science claims, and finally medicine and health. CFI Okanagan was established in July of 2010. Since then, it's grown and boasts over 50 active members, and it's growing all the time. If anyone's interested in membership information, please talk to Edmund, who's very friendly, but we keep him outside just in case. CFI Okanagan is based here in Kelowna, but its catchment area includes the entire Okanagan. And there is also a satellite group forming in Nelson, which is CFI West Kootenay, so we're very excited about that. Now, one of the major public functions that religious organizations perform is explicit acts of charity. This event today is part of CFI Okanagan's Good Without God series. It's designed to give members of the atheist community an opportunity to give back in much the same way that religious communities do. We had a winter clothing drive in December, which benefited In From the Cold and the Boys and Girls Club. And there will be a second one in July for the local food bank called Christmas in July. Now, there are perhaps few public health topics that stir up more controversy and argument than vaccination. Some of us here may remember a time when infectious diseases like polio, measles, and scarlet fever were just part of childhood. Now, of course, I say some of us, but I don't. Yeah, but these are illnesses that, I mean, all joking aside, these are illnesses that killed thousands of children and left many, even of the survivors, with lifelong disabling scars. Recently, however, vaccines have come under a great deal of scrutiny in the public. Questions have arisen about how safe it is to give children vaccines, what goes into them, how many vaccines are acceptable, how many are tolerable, and whether or not people should be exercising and are allowed to exercise their individual rights to choose not to vaccinate. And these are important and complex issues, and they deserve rigorous study that's based on solid evidence. Today, our panel is going to be tasked with giving you the facts that will allow you to make an informed choice about your own health, about the health of your family, and the health of your communities. Each of our panelists are going to present the facts about vaccines so that you have enough information to make up your own minds. We're going to have 6 presentations today from a variety of perspectives. At the end, we'll have a general Q&A where you can ask any of the panelists or the entire panel any questions that you may have. I will be, just fair warning, I will be cracking the whip. It takes 30 seconds or less to ask a question. If it doesn't have a question mark at the end of it, then I'm going to be stepping in and getting all mad. So keep that in mind. It brings me great pleasure to introduce Dr. Jenna Kluftinger, who will be talking about the history of vaccines. Dr. Kluftinger is a continuing special instructor in biology at UBC Okanagan, and teaches in the Southern Medical Program as well. She instructs in microbiology, immunology, biochemistry, and biochemical basic disease, as well as anatomy and physiology. Janet has described to me her passion for golf, which she describes as more of a nice walk with a stick and a ball thrown in for fun. So please join me in welcoming Dr. Kluftinger.
Okay, thank you very much. Let me know if I need to be putting on a microphone. I usually use them, but being this is a small room, I think I'll take my chances here. As Ian mentioned, I am giving a talk today on the history of vaccines, and I'll begin by giving you just a few definitions so that as we move forward with the day, you can be fully understanding some of the terms that are used. Immunology is the branch of science that deals with the immune system and attempts to understand the many phenomena that are responsible for both innate and acquired immunity. Now, innate immunity, that includes molecular and cellular mechanisms that are basically pre-deployed before an infection, and they're poised to prevent or eliminate the infection in a very non-specific way. So this would be things like your non-specific surface defenses, things like your skin, or the hydrochloric acid which is found in your stomach, those kinds of things. Acquired immunity, this is also called adaptive immunity, and that is the type of immunity that develops in response to an infection and adapts to recognize, eliminate, and then remember the invading pathogen. And the key part of that is, in terms of vaccinations, is the memory component. So when we are exposed to a particular microorganism and your immune system learns to recognize that that particular organism and react to it, it can prevent you from becoming ill with the same organism again. And that's the way that vaccines work as well. And Deanna Gibson is going to go into a lot more detail on that for you in the next talk. So immunity, that's the state of protection from infectious disease. It's from the Latin term immunis, which means exempt or exempt from a particular illness. You're immune. Your immune system is the remarkably adaptive defense mechanism that has evolved in vertebrates such as mammals, human beings, to protect from invading pathogenic microorganisms and from cancer as well. And indeed, we're coming up now with some vaccines against particular types of cancer, and I know that Dr. Godsell will be talking to that as well. Pathogen, that's any virus, bacterium, or other agent that would cause a particular disease. So where did the discipline of immunology come from? Basically, it grew from the observation that individuals who had recovered from a certain infectious disease were thereafter more resistant to that disease than were people who had never been exposed to it before. And in fact, there's many historical references to people beginning to understand the idea of immunology and being immune and developing immunity to a particular microorganism. Being sort of egocentric human beings, we tend to focus on things that affect us. So a lot of early history relates mainly to human diseases. So in Athens, 430 BC, we have records of plague, and at that time they knew that only people who had had the plague before and subsequently recovered should actually be nursing the ill, because they would not subsequently become ill themselves. And so that was one of the earliest references that we have to the recognition of something like immunity. There's many others, biblical references to lepers, plagues, Middle Ages, the bubonic plague, Black Death, where 25 million people died. Central America in the 1500s, where the Spanish imported smallpox and 90% of the Incan population perished as a result of that. 1918 influenza epidemic, where at least 20 million people worldwide perished. So in those early times, there was no understanding of the causative agents for disease. And in fact, the prevailing belief at that time was that that illnesses were caused by basically an imbalance in your body humor. So an imbalance between things like blood, phlegm, yellow bile, black bile was what was causing disease, or that it was toxic vapors called miasmas or something like that. And because there was no little or no understanding of what was causing disease, they didn't know about microorganisms, there were few treatment options. You know, isolation of patients, destruction of contaminated material, you know, use of some natural medications like plant products and that kind of thing. Because much of the early vaccination studies focused on smallpox, we're going to start with a little background information on this devastating disease. It is believed to have originated over 3,000 years ago in India or Egypt, and it is one of the most devastating diseases known to humanity, caused by a virus which is called variola major, and it does cause extremely serious illness, death in about 30% of cases, disability and disfigurement in 65 to 80% of those who manage to survive the illness. For centuries, there were repeated epidemics sweeping across continents, decimating populations, such as the Incan population, where, as I mentioned, 90% of the individuals perished, and changed the course of history, basically. And no effective treatment for this was ever found. So prevention, very key point here. So early vaccination studies in the 15th century in China and Turkey, they would take crusts from individuals who had had smallpox. They would dry them out and grind up the crusts, and then have people inhale them into their nostrils or insert them into a small cut in the skin. And this was called variolation, and it would prevent later acquisition of the disease. And in fact, in 1718, due to the success of this, Lady Mary Wortley Montagu, who was the wife of the ambassador in Constantinople in Turkey, she observed the positive effects of variolation and actually had this technique performed on her children. And this brought the technique of variolation to Europe. So eventually it did spread to Africa, Europe, and the Americas as a method of potentially controlling smallpox. Now, the results, however, were sometimes fatal. 2 or 3% of those variolated actually ended up contracting smallpox and dying as a result. But this is in contrast to the 20 to 30% of individuals who would die if they contracted smallpox naturally. So obviously not a perfect method, but it was the forerunner of what we now know as vaccination. In 1798, there was an English physician named Edward Jenner, and he noted that milkmaids who had contracted cowpox infections were subsequently immune to smallpox. So cowpox produces these multiloculated vesicles on the udders of cows, and when the milkmaids would go to milk the cow, those vesicles would break and the fluid would get on their hands, and they would develop a case of cowpox, which is relatively mild and didn't cause them much discomfort. But what Edward Jenner recognized was that these young people who were milkmaids were subsequently, they seemed to not ever come down with smallpox, and he wondered whether there was a link there. So he performed what is absolutely sort of a turning point in terms of immunization studies. And it should be noted that clearly if he performed this experiment today, his medical license would be revoked, and he would find himself the defendant in a very spectacular malpractice lawsuit. But what he did at the time was he transferred material from cowpox lesion on the hand of a milkmaid who was named Sarah Nelms, and he transferred that to a scratch on the arm of a boy named James Phipps. And James Phipps developed a local reaction, redness, itching, swelling, and felt poorly for a few days, but he did fully recover. And then 6 weeks later, and this is the part where it gets really a little touchy in terms of ethics, Jenner deliberately exposed Phipps to pus from a fresh human smallpox sore. And Phipps did not develop the disease and was determined to be immune. So this technique of inoculating with cowpox to protect against smallpox spread quickly throughout Europe. We now know that the cowpox virus belongs to the orthopox family of viruses, and those viruses include monkeypox, variola viruses, and cowpox, obviously, but they're closely related enough to each other that inoculation with cowpox your immune system will learn to recognize that, and it will allow your immune system to react to smallpox and eliminate it before it causes disease. This is a picture of Jenner, a painting that was done vaccinating James Phipps. And in fact, in the last decade of Jenner's life, he was actually able to see some of the fruits of his labors. The London Bills of Mortality documented in the last decade of his life 7,858 deaths from smallpox, which was down from 18,447 deaths in the decade before vaccination. So it's a huge reduction there. So in 1857, between 1857 and 1864, Louis Pasteur, who was a French chemist, physicist, and ultimately he became a biologist as well, he came up with the germ theory of disease, and this is where microbes, the theory states that microbes can invade other organisms and cause disease. This may seem very simplistic to us, but at the time, in these days, they didn't even have the ability to see microorganisms. These things are so small you can't see them with the naked eye. And so, coming up with the idea that something that you can't see is causing you to become ill was, not an easy thing for these people to accept. Pasteur succeeded in growing the bacteria that's thought to cause foul cholera in the lab and confirmed that it would cause disease when he injected it into healthy chickens. Now, he studied chicken cholera and developed a procedure for attenuating or weakening organisms for use as protection against subsequent disease. And it was kind of serendipity that came into play here. So he was leaving on an extended vacation, and he instructed his lab assistant that while he was gone, the lab assistant should inoculate a group of chickens with cholera. Now, luckily, the assistant actually forgot to do that, and then realized his mistake right before Pasteur was coming back. And so he quickly realized, I don't have a fresh batch of the bacteria, so I'll just use this batch that's been sitting around here for a couple of weeks. And so he used that, injected the chickens. The chickens became a little bit ill, but didn't actually die, much to everyone's surprise. Subsequently, when Pasteur got back, the available supply of chickens was apparently a bit limited in the lab, and not one to waste a good chicken. Pasteur grew up a new batch of the cholera bacteria injected into the previously treated chickens, and very unexpectedly, the chickens were completely protected against the disease. So basically, he hypothesized and proved that aging had actually weakened the virulence of the pathogen, and as such, this attenuated strain might be administered to protect against the disease. He later coined the word vaccination, which is from the Latin facet for cow. That was sort of a nod back to the experiments of Jenner and the cowpox virus that caused us to name this particular technique vaccination. In 1881, Pasteur vaccinated one group of sheep with heat-attenuated anthrax bacteria, and then challenged the vaccinated sheep with some of the unvaccinated sheep with a virulent culture of the anthrax bacillus. All the vaccinated sheep lived, all the unvaccinated sheep died. So it was pretty clear that the attenuated anthrax bacteria vaccine was protecting these sheep. In 1885, Pasteur developed a rabies vaccine made of dried spinal cord from rabbits that had been infected with rabies. And this young man here, Joseph Meister, was the first person to be immunized against rabies. In 1885, he was 9 years old, and he was bitten by a rabid dog, and quite badly bitten. Now, in those days, being bitten badly by a rabid dog was equivalent to death. You were going to die as a result of that. There was no treatment for rabies, and virtually 100% of people who were bitten by a rabid dog severely would perish as a result of that. Joseph Meister's parents had heard that Pasteur had been working on a rabies vaccine. They brought their son into the lab, and they begged Pasteur to give him the vaccine. Pasteur, the story goes that he had to think about it. He thought about it for a day. He went home and considered his options. It was very controversial because he was not an MD, and no humans had been successfully inoculated against rabies in the past. But realizing that this young man basically had a death sentence on his head, he decided to go ahead and do it. So he did use the rabies vaccine on Joseph Meister, and Meister survived as a result of that. As an adult, Meister served as the caretaker at the Pasteur Institute until his death in 1940 at the age of 64. And it was during the Nazi occupation of Paris that he committed suicide by shooting himself with his World War I service revolver. Reports vary, but some claim that he chose to commit suicide rather than allow the German forces to enter Pasteur's crypt. So further developments. At the dawn of bacteriology, many crucial developments in immunization rapidly followed the work of Pasteur. So between 1920 and 1940, antitoxins and vaccines against things like diphtheria, tetanus, anthrax, cholera, plague, typhoid, and tuberculosis were developed. The middle of the 20th century was particularly active time for vaccine research and development because they had better methods for growing viruses in the lab. They had rapid discoveries and innovations, including the creation of vaccines for polio. Researchers targeted other common childhood diseases such as pertussis, which is whooping cough, measles, mumps, and rubella, which is German measles. And the vaccines for these diseases reduced the disease burden greatly as a result. To this day, scientists work to improve the efficacy and safety of the present vaccines and to develop new vaccines designed to target microorganisms that spread global death and disaster. But what's the nature of these microorganisms that we are trying to counteract? Basically, most human pathogens can be grouped into 4 major categories: the viruses, bacteria, fungi, and parasites. Parasites range in size from protozoa, which are very tiny, microscopic, to arthropods and to tapeworms, which can be up to 10 meters in length. And the pathogenesis just vary from microorganism to microorganism. If we just take a quick look at what some of these look like. Rotavirus, this is an electron micrograph of rotavirus. It accounts for 600,000 infant and childhood deaths per year worldwide. Particularly, this is prevalent in developing countries. This is Clostridium tetani, which is a bacteria that causes tetanus. It is a bacteria that is capable of forming endospores, and those endospores are very, very resistant to killing. Clostridium tetani spores can be found in soil. You can go in your garden and grab a handful of soil. You're likely to come up with some Clostridium in it, or at least it's not unlikely. The organism, the spore, enters the skin through a cut in the skin, and subsequent to that, if the spore germinates, it can produce a toxin. The toxin causes basically uncontrolled stimulation of the skeletal muscles, and so you end up with rigid muscle spasm, and that includes the jaw muscles, and that is where we get the lay term for tetanus, which is lockjaw. And death can result from spasms of the respiratory muscles such that the individual can no longer breathe. And this is actually a portrait of an individual suffering from tetanus. The muscles have contracted to the point where the person is entirely rigid, and you can see the rigid facial muscles there. Fatality rate in generalized tetanus ranges from 30 to 90%. Because tetanus treatment is not very effective, and therefore prevention, which is possible via vaccination, is all important and depends on immunization. This is just an example of a yeast, the third category there. This is Candida albicans, which commonly causes oral rash or thrush or vaginitis in immunocompromised individuals or those who have taken antibiotics. Malaria parasites. So this is an example of a parasite. Malaria is a life-threatening disease caused by parasites that are transmitted to people through bites of infected mosquitoes. And in 2010 alone, malaria caused an estimated 655,000 deaths worldwide. You can see the parasite here. Vaccination or immunization, that is the intentional administration of harmless or less harmful form of a pathogen to induce specific immune responses that protect the individual against later exposure to the same pathogen. And vaccine is defined as the preparation of the antigenic material used to induce immunity against the pathogenic organisms. So let's look at the vaccination program implementation and the results that we have seen historically since we started vaccinating regularly. Basically, there are a few measures in preventative medicine that can compare with the impact of vaccines. If you look at this is the cases of selective infectious disease before and after the introduction of effective vaccines in the USA. The annual number of cases per year prior to vaccine would have been 48,000 plus some change there. Post-vaccine, it is down to 0. Smallpox has been eradicated, and we're going to talk a little bit more about that on subsequent slides. Polio, if we look at polio here, you can see that in the US it has been eliminated, and it is on the verge of eradication worldwide in most countries around the globe. Measles has been controlled or eliminated in numerous countries around the world, although we are still seeing breakthrough there, and I'm going to talk a little bit more about that later on. But you can see from this that the incidence of things like diphtheria, measles, mumps, pertussis, or whooping cough, rubella, which is German measles, poliomyelitis, tetanus, have declined dramatically as a result of immunization. Smallpox has been eradicated. There have been no naturally occurring cases since October of 1977. And they are predicting eradication of polio if we can manage to maintain the large-scale vaccination programs. We were very close to eradicating polio, but it was delayed by a temporary suspension of vaccinations, which occurred in Nigeria and some areas of India. And then there was a resurgence of polio in those areas. That illustrates what happens when we do become complacent about our vaccination protocols. So let's look at how we actually got to the eradication of smallpox. In 1967, the World Health Organization launched an intensified plan to eradicate smallpox. They had the global eradication campaign, and it was smallpox was finally pushed back to the Horn of Africa, and then there was the single last natural case which occurred in Somalia in 1977. Global eradication of smallpox was certified by a commission of eminent scientists in December 1979, and subsequently endorsed by the World Health Assembly in 1980. Smallpox had previously been considered to be the ancient scourge that threatened 60% of the world's population, killed every fourth victim, and scarred or blinded most of the survivors, and it eluded all forms of treatment. This is a picture of an African child with a rash typical of smallpox. Again, the last known case of naturally acquired smallpox was in Somalia. Subsequently, there was one fatal laboratory-acquired case that occurred in the United Kingdom in 1978. It was basically a woman named Janet Parker, who was 40 years of age at the time of her death. She was the last person to die of smallpox, and she worked as a medical photographer in the anatomy department at the University of Birmingham Medical School. And she died after being accidentally exposed to a laboratory strain of smallpox. She worked in a dark room above the labs that were working with smallpox, and the smallpox went up through a vent that was connecting the two floors. Her mother also contracted smallpox from her daughter, but the mother survived, and unfortunately Ms. Parker passed away as a result of that. These events actually led to the suicide of Professor Henry Benson, who was the then head of microbiology at the University of Birmingham and felt personally responsible for this woman's death. And it also led to increased safety in labs that were dealing with smallpox. This shows the reported annual number of cases of rubella, polio, pertussis, mumps, measles, and diphtheria in the USA in the peak year compared to the number of cases in 2004. So you can see the drastic reduction. Polio to zero, diphtheria to zero, mumps, measles, rubella significantly reduced, and even pertussis reduced as well. Now, at that time, the pertussis vaccine had some significant problems with it. We now have a much safer vaccine. This is the progress toward worldwide eradication of polio. You can see in 1988 the distribution of polio, and you can see in 2005 it's been pushed back. And again, certain areas of Nigeria and India, we're still seeing cases because of the temporary suspension of their vaccination protocols. To put it bluntly, there are more than 8 million people who would otherwise have been paralyzed that are walking today because they have been immunized against polio since the initiative began in 1988. So that's 8 million people who can walk today. Okay, this shows us, sadly, although existing vaccines could save the lives of millions of children in the developing world, political and economic issues prevent the distribution of such vaccines to the people who need them most. There are safe, effective vaccines for 5 of the top 10 killers of children: pertussis, tetanus, measles, pneumococcus, and Haemophilus influenza. There are vaccines that could prevent these deaths. Administration of these vaccines that are recommended for infants in Canada could cut the child mortality in the world by approximately half. And if you look at the number of deaths here, I want you to bear in mind that this is death in the thousands. So literally there are, if we look down here to tetanus, for example, 201,000 children annually die of a completely preventable disease. This shows us the introduction of measles vaccine in 1962, which led to the dramatic decrease in the annual incidence of this disease in the USA. You can see that there was a little peak in here, and we do see occasional outbreaks occurring mainly among unvaccinated children and college students who only received one vaccination when they were very young, so we do see it coming back. This shows the incidence of Haemophilus influenza, type B disease, since the introduction of the vaccine. Rate per 100,000 children, 40, dropping right down to close to 0. So we've just seen a few examples of how our global society has benefited from our vaccination programs, but have these gains come without a cost and a risk? No. There were production problems in the early vaccine that led to some serious adverse outcomes. And even today, there is still a very small risk of potential adverse side effects of our existing vaccines, for example, rare allergic reactions. But even those that occur in a very low frequency must be carefully considered and must always be balanced against the potential benefit of protection by the vaccine. Scrutiny in terms of safety and efficacy of our existing and experimental vaccines must be both thorough and ongoing. In many ways, the vaccination programs in North America, however, have become a victim of their own success. Some parents who have never encountered the diseases now nearly vanquished in our society do not consider it important to have their infants vaccinated or may not adhere to the recommended schedules of immunization. Our grandparents, they knew the importance of vaccination. They had firsthand knowledge. They had actually seen the many individuals who died or were severely and permanently disabled by these horrific diseases. What is important for us to remember is that with the exception of smallpox, these diseases still cause death and disability in our world. Without a microscope, we can't see these deadly bacteria and viruses, but they are still there. We are just keeping them at bay with our vaccination programs, and we can't let our guard down now. Protection of the individual and of our society depends on the continuation of our immunization programs. So in conclusion, in medicine, the greatest triumph of immunology has been vaccination or immunization, a procedure whereby severe disease is prevented by prior exposure to the infectious agent in a form that is extremely unlikely to cause disease. Vaccination provides the opportunity for your immune system to gain the experience needed to make a protective response with little risk to health or life. And our next speaker, Dr. Deanne Gibson, is going to explain to you actually how vaccines work.